we need to go through a bunch of material here. I don't want to get too bogged down. So let's try to do this without the mechanism. Can anyone propose, what do you think is, what's going to be our product here?
Well, it's going to reduce the carbonyl alcohol.
Right. That's it. All right, if we had more time, we'd go through the whole mechanism, but this is something we should have done in the past, or it's also in the videos. What's kind of starting material are we starting with here?
Carbonyl ketone.
Yeah, we want to be more specific. This would also work on an aldehyde. So this is an aldehyde or a ketone. This is a category 1 reaction. Remember, nucleophilic attacks there are category 1. So basically what happens here is the H- attacks, that put in this H, and then we do a protonation step. All right, so you should know the mechanism for that, but we won't go through that right now. By the way, this would also work, just to back up for a second, this would also work with sodium borohydride. This reaction would also work with sodium borohydride. By the way, who's more reactive, sodium borohydride or lithium aluminum hydride?
Lithium aluminum hydride.
Yeah, but either of them could do this reaction.
And then if you want to be extremely less reactive, use dipole.
That's right. That's good that you know that. We might not have time to go through those today, but it's good that you've seen that. Okay. We will just try to stick to the lithium aluminum hydride. All right. Well, can anyone just propose in words, what's the product going to be here?
An aldehyde.
An aldehyde? That seems very logical.
No, isn't it just going to be an alcohol?
Oh yeah,
and that's also logical.
Continues.
So those are both logical suggestions. So you're both right. First an aldehyde, then an alcohol. Although it's a little more complicated than that, but so at first we would think that this H- nucleophile would just replace the OH in an addition and elimination reaction. Now we're attacking, what type of functional group did we start with?
Carboxylic acid.
Yeah, so we would expect a normal addition elimination where we just replace the L group. We replace the OH with an H. But didn't we just get finished saying that aldehydes and ketones also get attacked by lithium aluminum hydride? So we would expect that to go further to the alcohol. This is an oversimplification. There's actually some complications here because the lithium aluminum hydride also tends to deprotonate this oxygen. So the mechanism is a little bit weird and complicated. But the upshot is this is the product. The upshot is that we will get an alcohol here. So we will get an alcohol. In fact, just to simplify, so as you figured out, this will be the product. Maybe I'll keep putting stars in for the carbonyls again. Okay, let's describe in words what the product would be here.
Wouldn't it also be an alcohol?
Yeah, and here we can definitely do what we proposed before. The initial intermediate would be an aldehyde. Here, definitely the H- will just replace the OR leaving group. But then it makes sense that the aldehyde would then get attacked in the category 1 reaction. And we get an alcohol. I just drew this for, I don't know, to first understand the mechanism, but this is the final product. The final product is the alcohol. All the aldehyde will be reacted. What starting material did we start with here?
An ester.
Yeah. So the mechanism is more is maybe a little different from an acid and an ester, but the end result is the same in both cases. In fact, everything, this is kind of boring, everything here seems to be reducing to an alcohol. In all these cases, we're reducing to an alcohol. Now let's describe in words what would the product be here.
Would be an alcohol with NH3.
Okay, that's a very reasonable suggestion.
No, it would be O minus. Wouldn't it?
That's another reasonable suggestion, but both of those turn out to be incorrect. Notice that up here, when we attacked here, we ultimately kicked off this OH group. The oxygen was a leaving group, and here the oxygen was a leaving group. But who is it easier to leave? Remember, something that leaves is somebody who leaves and takes their electrons. Who would rather leave and take their electrons, the oxygen or the nitrogen?
Like oxygen, because it's more electronegative.
Yeah, it's easier for an oxygen to be a leaving group because it's more electronegative. It would rather leave and take its electrons. So it's not the NH2 that's going to be leaving here. It's the oxygen. This is kind of an oversimplification of the mechanism. We just won't have time to do the mechanism for this.
This is how you make amines.
That's right. All right, now the plot finally becomes clearer here, how we can use this to make amines. All right, so this is a reaction that maybe we should... Sorry?
Sorry, it's the OH, H2O that falls off? Or like what's...
Well, at some point this will fall off.
Yeah.
That's right. It's a bit of a complicated reaction, and we just won't have time to go through the mechanism for that. But basically, these hydrogens push off this oxygen. Notice that right here, keep putting in our stars.
It falls off just as like...
Notice that this oxygen is connected by 2 bonds to the carbon. But we're gaining here 2 hydrogens. So those hydrogens end up completely kicking off the oxygen. And we won't go through the details. But maybe it's not too surprising that the oxygen leaves instead of the nitrogen, because oxygen is a better leaving group than nitrogen. Maybe I shouldn't press that too far. In a way, you kind of have to just memorize this. Maybe this doesn't make too much sense. Maybe you just have to memorize this. This should really surprise us, because notice the nitrogen is not acting like an L group here. The nitrogen is not acting like an L group. It's not leaving, even though we said in the past that this always would be the L group. So this is really just has to be memorized as an exception to what we learned previously. This really just has to be memorized as an exception. Based on what we've said previously, we would expect the nitrogen to leave. I tried to give an explanation for where the oxygen left, but maybe I shouldn't press that too far. Maybe we just have to memorize that in this case, it's the oxygen that leaves and not the nitrogen. Now, a couple of other points. Where did these hydrogens come from? Well, is this carbon electrophilic or nucleophilic?
Electrophilic.
And is this oxygen electrophilic or nucleophilic?
Nucleophilic?
Because it's got a lone pair. The nitrogen, the oxygen is nucleophilic with its lone pair, and the carbon is electrophilic. So, what type of hydrogen would attack the carbon? Nucleophilic or electrophilic?
Nucleophilic.
And what type of hydrogen would attack the oxygen? Electrophilic. That's right. Now, what type of hydrogens are these?
Nucleophilic.
And what type of hydrogen is this?
Electrophilic.
That's right. So where did this hydrogen come from? The hydride or the, sorry?
Hydride.
This came from the hydride, and this came from the hydride, and this came from
Acid.
the acid.
Right. Like if you were to just put it in LiAlH4 without the H3O+, it would be O minus.
That is correct, because we would not get this last step. That's a very important point. Without this last step, there would be nothing to protonate it, but these 2 hydrogens would still show up, because they didn't come from the H3O+.
So how come in this case it doesn't just turn into an O minus?
That's a good question. So, where did this hydrogen come from?
LiAlH4.
Because it attacked a carbon. And where did this hydrogen come from?
LiAlH.
Right? And notice, since we don't have any oxygen left, we don't need any electrophilic hydrogens. We needed the electrophilic hydrogens here to protonate this oxygen. But here the oxygen is gone.
Yeah, but you needed it to protonate the oxygen that became negative when you added the LiAlH4. So in this case, why doesn't the oxygen become negative when you add the LiAlH4?
Yeah, you would think that. But actually, I think what happens is that instead of being protonated, the oxygen forms a complex with the aluminum that stabilizes it. Yeah, so again, we're not going through the full mechanism here. Those are good points there. So you're right, we need something to stabilize the negative charge on this oxygen. I think that if you actually look at the full mechanism, it'll be stabilized by forming some kind of complex with the aluminum over here. So that was a good point. But it turns out we really are not going to ending up having to protonate this oxygen here. All right, so this reaction doesn't need any acid. This reaction doesn't need acid because there's no oxygens left to protonate. So it's hard to sometimes for people to remember when you need the acid and when you don't, but I tried to explain why that was the case here. Because here the oxygen is gone. All right, now you want to carefully compare these two cases because it's easy to confuse them. So notice in this case, basically the OR group gets kicked off and this oxygen stays around and turns into an alcohol. But in this case, it's the oxygen that gets kicked off and the nitrogen sticks around. So we don't want to confuse these two cases. This is the case that makes sense. This is the case that fits into our previous patterns. And the amide is the exception that we just have to memorize. And as somebody already said, aha, now we've thought of a way to make amides. This is a way to make amides.